Welcome, everybody. Come on in and sit down if you're standing. Welcome to the last session of the day. Thank you for sticking it out. We have here Mia to talk to us about the most bizarre software bugs in history. So I want you all to give a warm welcome to Mia.
We've been all told that we should test our software, but what happens when we don't? Sometimes it leads to strange and unexplainable events. Is testing more always the right solution? What do bugs reveal about software? And how can we use these lessons to build more resilient systems? Let's take a look at the most bizarre software bugs in history. It's 2018, the airport in Jakarta wakes up. The sun rises over horizon, planes are heading to the runway. Everything is as usual. Inside one of the planes, two pilots sit in the cockpit. Nothing unusual. They've done this a ton of times. Together, they got over 5,000 hours of flying under their belts. They go through the pre-regular pre-flight checks. Everything looks fine. Instruments are good. Weather's great. No issues at all. The plane heads out to the runway. Engines start roaring, it picks up speed, and they're in the air. Everything is smooth. A few minutes later, the pilots reach for the controls. Something feels off. The nose of the plane suddenly dips. They didn't do that. The captain pulls back on the controls, the nose lifts, and for a moment, everything seems fine. Maybe it was just a turbulence. Nope, it dips again. A warning flashes. Airspeed disagree. What does that even mean? They have no idea. They check the dashboard, they go through the emergency checklist, but neither of them really know what's going on, and they're 5,000 feet in the air. They try to pull the nose up again, but the plane is pushing back. It feels like they're fighting against the controls. Like someone or something else is flying the plane. The plane races towards the ground at full speed, and then, at 11 p.m. 32 minutes, Lion Air Flight 610 disappears from radar. What were the pilots actually fighting? Was it the turbulence, the engine, the controls, or was it something else? Maybe just a few lines of code. To find out, let's go back to year 2010. As most of you already know, the biggest aircraft manufacturers are Airbus, based in Europe, and Boeing, based in the US. And they've been competing for decades. In 2010, Airbus made a big move. They announced the A320neo, as you can see on the right side. It was an updated version of their best-selling plane on the left side, and it had the same design, but bigger and more efficient engines. As you can see here, it looks exactly the same, but with just bigger engines. What that meant was that the fuel costs were lower, and the operating costs were also lower. So airlines loved it. Within months, Airbus received thousands of orders. And Boeing had a problem. Their best-selling plane, the 737, was less efficient and more expensive to fly compared to A320neo. So they had two choices. One, they could design a brand new plane which could take years. Or two, they could also modify the existing 737 and make it more competitive. So they chose the second option. In 2011, Boeing announced the 737 MAX. The idea was simple. Put bigger engines on it, just like Airbus did. But there was one problem. If you compare Boeing to Airbus, you'll notice something. The 737 sits lower to the ground, as you can see on the right side. So that means that if you just want to put the bigger engines, they cannot fit under the wing. So how do you fix this problem? They came up with a very interesting and very unique idea. They moved the engines forward so they would fit. However, when you move the engines forward, what happens is that you also shift the plane's balance. Why? Well, obviously, because the engines are the heaviest part of the plane. So if you move the heaviest part forward, the aircraft's center of gravity shifts, making it more likely to tilt. Now, this necessarily isn't a problem. If you're an experienced pilot, you generally know how to control a plane that has a tendency to tilt, so it's not an issue at all. But there's one catch. If you release a plane that behaves differently, you need to train pilots so they know what to expect and how to react if something goes wrong. And pilot training takes time, sometimes months, sometimes years. But Boeing didn't have time. They were losing the market race, so they came up with a very interesting idea. Instead of training the pilots, why not add a piece of software that makes the plane behave exactly like the previous version? So they invented the maneuvering characteristics augmentation system. The way it works is that if a plane's nose tilts up, the system corrects it by pushing down. Pretty simple. Now, there is one catch. All without the pilot knowing that this software is controlling the plane. If you're driving a car, imagine that your car just moves unexpectedly to another lane without you controlling it or knowing what's happening. And there's a simulation on YouTube where they put an experienced pilot through the same conditions, and they described it as, it's a horrible situation, it's unimaginable. Now, let's take a step back. How do you determine the position of a plane's nose? In aviation, the industry standard is that all sensors measuring critical data, like speed or position, must be duplicated. If both sensors give the same reading, as you can see here, it is considered correct and displayed to the pilot. But if two sensors give different results, like in this case, then the pilot is alerted and follows a specific checklist of actions to resolve the issue. And for each issue, there's a checklist. MCAS, however, relied on a single angle of attack sensor to determine the plane's position. Why? Well, we don't know. It's not documented in any official reports, so most likely it was a management decision, probably to reduce costs or complexity. So let's put all of these pieces together. What happened with Lion Air Flight 610? Boeing added a piece of software to automatically adjust the plane's position if it tilted too much. The software relied on a single angle of attack sensor. That one sensor was failed because it was miscalibrated, so it was sending incorrect data to the system. The software got activated unnecessarily and forced the plane's nose down. The pilots didn't know that it existed, and they didn't know how to disable it. Now, some of you might be wondering, has this plane ever been tested? How is it possible that no one knew what's happening here? Did anyone really know? Well, in March 2017, the Boeing 737 MAX received certification from the Federal Aviation Administration. And the official statement said, to earn certification for the 737 MAX 8, Boeing undertook a comprehensive test program that began just over 1 year ago with 4 airplanes plus ground and laboratory testing. Following a rigorous certification process, the FAA granted Boeing an amended type certificate for the 737 MAX 8, verifying the design complies with required aviation regulations and is safe and reliable. But after the crashes of Lion Air Flight 610 and one more flight, investigators found something very alarming. It turned out that the FAA had delegated large parts of the certification process to Boeing itself. So Boeing was reviewing its own work. So that meant that critical safety systems were never properly evaluated by an independent authority. Instead, Boeing engineers signed off their own safety reports. After the crashes, the 737 MAX was grounded worldwide, and in response, the FAA identified 8 critical safety issues that had to be fixed before the plane could fly again. And Boeing was also charged with fraud for misleading regulators. So they made several changes to fix the problems that led to crashes. 2 sensors instead of 1 to mitigate a single point of failure. The software does not activate repeatedly. The movements of the software are limited. There are better pilot training and new emergency procedures. There's a warning always turned on in case something goes wrong, and there are new calibration checks for sensors. As you can see, it's never just one thing that causes failure in complex systems, and in risk management, this is called the Swiss cheese model. Imagine you have slices of Swiss cheese with holes in them. One hole by itself does not matter, because there is no hole in the next layer. But sometimes you can get unlucky. All the holes line up, and that's when failure happens. So in this case, the software had a flaw, the pilots weren't trained on it, so there was a human error, and there was a mechanical failure. The plane had only one sensor, and that one sensor failed. And all of this by itself might have not caused a disaster, but when all of them aligned together, that's what made it deadly. So what does it mean to us? Is it only in aviation and in critical systems? Well, actually, this model applies to all complex systems. So why is it hard to catch these kind of failures? Well, it all comes down to combinatorics. So if you have one input, you have one output. If you have 5 inputs, you have 120 possible outputs. 10 inputs over 3 million outputs. And this is all assuming that your system is deterministic. And now, think about modern software. How many lines of code are there? How many people work on it? How much of infrastructure is involved? From writing a piece of code locally to running it on a production server, there are 1,000 things that could go wrong. So what can we learn from this story? First, single points of failure are dangerous. Failures are often a chain reaction. Software should never do something users aren't aware of. We've just talked about how failures, when combined, can lead to a disaster. But sometimes a single mistake is enough to cause worldwide disruption. Imagine this. You're a developer at Google, it's a normal day, you push a simple update to Google Safe Browsing, the system that warns users about dangerous websites. A very small change. Nothing unusual. And then you realize that every single website on Google is marked as dangerous, including Google itself. And that's exactly what happened in 2009 when a Google engineer made a tiny typo. For 40 minutes, every Google search result said, "This site might harm your computer." And the funny thing is there's just one service that was not affected, and that is the ads. Why? No idea. Ads always work. So what went wrong? One of the engineers was updating the malware registry, a list of dangerous websites, and instead of entering a specific URL, they accidentally added just one character, a /, which in technical terms means everything. So what we can learn from this is that typos happen, and sometimes testing more is the answer. And if you don't test, sometimes it can lead to costly mistakes, like the one that cost NASA $327 million. September 1999, NASA's Jet Propulsion Lab, Mars Climate Orbiter finally reaching its destination. The Mars Climate Orbiter was a robotic probe about the size of a small car, and its job was pretty straightforward. Cruise to Mars and orbit the planet to study Martian weather and climate. Think of it something like a weather satellite for Mars, no astronaut on board, no people, just lots of sensors and lots of electronics, as you can see on this image. The team had been working on it for years, and it cost hundreds of millions of dollars to build and launch. So back then, it was a pretty much of a big deal for NASA. After 10 months of traveling, the orbiter finally reached its destination. It was on all TVs, and everyone had been waiting for it for years. The orbiter fired its engines to enter orbit. Then it was supposed to come out from behind the planet and radio back saying, "Hey, I made it." But instead, there was silence. No signal. Minutes passed, hours, and still nothing. The Mars Climate Orbiter had essentially vanished. So, what happened? At the beginning, no one knew. It was supposed to be 110 kilometers from Mars. But instead, they found out that it had dropped to 57 kilometers, so low that it was basically grazing the mountain tops. And at that altitude, the Martian atmosphere tore it apart. The spacecraft burned up or broke into pieces, completely destroyed. But the question is, why did that happen? What could have pushed it so far off course? The spacecraft was built by an external contractor on the left side, and it was operated by NASA's navigation team on the right side. There was a piece of software that calculated the force of thruster firings, and it was integrated with the navigation software that was reading this data. So there was a software between those two teams that was connected. When they checked the numbers, all the numbers were right. But then they realized that the meaning of those numbers was off by a factor of 4.45. And then they realized where the problem was. The first software output those values in pound/seconds, which is imperial measure of impulse. But the navigation software reading the data assumed it was in Newton seconds, which is metric. Over the course of the mission, every time the orbiter's small thrusters fired to adjust its course of orientation, the recorded impulse was misinterpreted. So you might be wondering, how did such a basic error flip through for a mission this important? And that's a great question. It was a communication failure because NASA's navigation team assumed everything was in metric. And the worst part of it, that the data had shown inconsistencies weeks before the failure. NASA had seen small navigation errors, but they weren't fully investigated. So what can we learn from this example? And I think this is a really great example because so many things are applicable to any kind of software. If two systems interact, make sure they agree on formats, units, and overall assumptions. Here, we had two systems interacting and operating under different assumptions. Here, it was just one bad assumption that broke down the whole system and a huge mission that cost so much money and so much time. Integration tests are useful. If NASA had simulated the navigation with the actual data units in place, they might have caught the discrepancy before launch, but they did not have any integration tests. And learn and improve processes. After this disaster, NASA standardized units across the organization, enforced stricter checks, and improved inter-team communication protocols. In the mid-90s, a new employee at Sun Microsystems in California kept mysteriously disappearing from the database. People started investigating only to discover that the issue wasn't a system failure. It was his name. His name was Steve Null. And it turns out that some systems back then didn't handle the string null properly. I tried to reproduce it in Postgres locally. I created a database and inserted the value null as a string. And as you can see, if I try to retrieve it, it works fine. But you can still find bugs like this in various systems. For example, I found an open issue in Apache Flex, which is a very old system, not used anymore, but you can find bugs like those. We've all heard of the urban legend, I have no idea if it's true, about someone who changed their license plate to drop database and attempted a SQL injection attack. And speaking of SQL injection attacks, I cannot not to mention that popular comic. Hi, this is your son's school. We are having some computer trouble. Oh dear, did he break something? In a way. Did you really name your son Robert Dog Table Students? Oh yes, little Bobby Tables we call him. Well, we've lost this year's student records. I hope you're happy, and I hope you've learned to sanitize your database inputs. Some automated systems will delete all records that start with test or ABCDE because they assume they're test data, even though they're not. If you are now thinking, who would give their kids such a name? Well, actually, I have some news for you. Between 1990 and 2020, over 300 babies in the US were named A, B, C, D, E. I can only imagine how well it goes with modern software. So, what can we learn from it? Handle edge cases in user inputs, because real-world data can surprise you. For a long time, we thought that the most expensive book ever sold was the Codex Leicester, written by Leonardo da Vinci in the 16th century. It was later bought by Bill Gates for $30.8 million in 1994. A book filled with the thoughts of one of the greatest history's minds, handwritten pages of scientific observations and ideas centuries ahead of their time. So, what kind of book would have to come along to be that record? Some rare manuscript, a lost work of literature, something of massive historical importance? Well, in 2011, a book appeared on Amazon with a price tag of $23.7 million. And no, it wasn't some ancient text or a long-lost treasure. It was a book about the genetic development of flies. And funnily enough, just like the bug of the cover, the price was a bug too. So here's what happened. On Amazon, third-party sellers can set automatic pricing rules that adjust their prices based on competitors. One seller set their rule to always be 0.07% cheaper than the next lowest price. Another seller had a rule to always be 27% more expensive than the lowest option. Normally, this works fine, but there are multiple sellers balancing out the prices. But here, there were only two sellers, and their pricing algorithms got stuck in a loop. So every time the system updated, one seller's price went up and the other fell even higher, again, until the book was listed for $23.7 million. As soon as people noticed, the system was fixed and the price dropped back to normal. So what can we learn from it? Be careful about your assumptions. Sometimes it's hard to say what is a bug and what is a feature. Take Excel, for example. Everybody uses it, even biologists. In 2016, researchers in Melbourne analyzed 18 genome research journals and found that 19.6% of gene studies contained errors. How is that possible? Well, did you know that there are genes called March5 or Sep15? Well, Excel didn't, so it auto-corrected them to a date. So, if 1 in 5 gene research papers had Excel-induced errors, how bad is it in the business world? For that, we turn to the European Spreadsheet Risk Interest Group, an organization that studies spreadsheet mistakes. And they estimated that around 90% of business spreadsheets contain errors. How did they come with that number? Well, in 2001, during the Enroll scandal, the US government released 500,000 emails from the company, many with spreadsheets attached. Researchers studied them as a real-world snapshot of how spreadsheets are actually used. And here are some fun facts. The average spreadsheet size was around 14 kilobytes. The average spreadsheet had around 6,000 non-empty cells. One spreadsheet had 174 worksheets. 6,000 spreadsheets contained no formulas at all, and 24% of spreadsheets with formulas had at least one error. And sometimes those errors cost a lot of money. JP Morgan used spreadsheets to calculate risk, specifically something called value at risk. Value at risk is supposed to answer the question, what's the most money we could lose in a single day with 95% certainty? It's based on historical price movements, volatility, and current portfolio positions. If the VAR is low, traders are allowed to take bigger risk, but if it's high, they need to play it safe. And one specific calculation at JP Morgan was done in a series of Excel spreadsheets with numbers manually copied and pasted between them. This was supposed to be a prototype, but instead it was put into production without being converted into a proper system. And the risk calculation was, of course, wrong. Now, there was a valuation control team whose job was to check if the traders were marking their portfolios correctly, but they were also using Excel, and those spreadsheets were also full of mathematical errors. And it got so bad at one point that one employee started their own unofficial spreadsheet just to track actual profits and losses. And by the time they caught the mistake, it was too long. And JP Morgan later published a report detailing what went wrong. After subtracting the old rate from the new rate, the spreadsheet divided their sum instead of their average. This error muted the volatility by a factor of 2 and lowered the value at risk. In other words, JP Morgan lost $6 billion because someone added two numbers together instead of averaging them. The biggest thing we can learn from it is that spreadsheets are code as well, and treat spreadsheets like production software. We've seen how software can cost millions, destroy spacecraft, but sometimes a bug doesn't wipe out a company or cause a disaster. Sometimes it just deletes your entire operating system. Bumblebee was a project designed to enable NVIDIA dual GPU support on Linux laptops, allowing users to upload graphics rendering to the discrete GPU. Everything was working fine until one update in 2011. A user created a GitHub issue with a rather urgent message. Install script does rmrf user for Ubuntu. That one extra space turned a command that was supposed to delete a specific folder into one that deleted the entire user directory, basically wiping out the core of the operating system. The author quickly pushed the fix with a comment message that really summed up the situation. Giant bug, causing user to be deleted. So sorry. Of course, this being open source, the community did not hold back in the comments section. How can you complain about bugs, Mr. Anderson, when you have no operating system? Bleeding edge really bleeding for someone now. No more lack of disk space now. I didn't like that folder anyway. I'm Mia Bajić. Thank you for your attention. I put together a list of resources I used for my presentation, and I have here my two favorite books about software flows, Humble Pie and The Design of Everyday Things. If anyone has any other book recommendations, I'm always happy for them. And that said, now it's time for Q&A. If we have time.
We have time for 1 or 2 questions.
Yep. What is the biggest bug you ever made?
I need to think about this one.
Okay.
Thank you for your question. It's a great question. So I'll be thinking about it, and I will let you know within the next 2 days.
Thank you for your presentation. Do you have any examples of an instance where the consequences of the mistake outperformed how it was intended to perform?
So when someone made a bug and it made it even more popular or better?
Yeah, something along the lines of that.
So yes, there is a game Civilization. And there was, people started making jokes on Reddit about it, that there is a bug. There wasn't a bug, but the game designers decided to introduce the bug because they thought it was funny, and then it became even more popular. So if you're interested into it, just Google Civilization game bug.
Thank you.
You're welcome.
Okay, thank you, everybody. Let's thank Mia one more time.